And we're back again for part 2 of our discussion of stoichiometry calculations. Hopefully some of you had some fun with yesterday's recipe calculations 5 and 6 and got those done. Again, I'll be asking you to turn the entire packet in as one assignment. It's caused a little bit of confusion when I've been breaking things up into multiple days, so we'll just do it all at once. Stoichiometry is difficult. It requires a whole battery of skills. You have to know how to calculate molar mass. You have to be able to convert from number of moles to number of grams, or from number of moles to liters, or to number of particles. So that's a whole bunch of different problems as well. Requires you to balance a chemical equation, which is another series of skills. You have to know how to use that chemical equation to find the mole ratio. It's just a lot of work. So it's really not mathematically hard, but it is, there's a lot of different problems in one. So when we're writing mole ratios, we have to know how to get them. We get them from our balanced equation, like I mentioned before. They're going to help us, that balanced equation is going to help you determine how much of the reactant, or plural reactants, you need, and how much of the product or products you can make. And it's just like a recipe. If you can kind of get that in your mind, that it's just really similar to like cooking, then you'll be on your way to success. So that mole ratio conversion factor comes from the coefficients in a balanced equation. So we're going to go back to our ammonia production. We've already talked about this is 1 nitrogen goes with 3 hydrogen to make 2 ammonia molecules. But you can also think of it as 1 mole of nitrogen for every 3 moles of hydrogen molecules. Another way to say that, right, just ignore the nitrogen, hydrogen, 1/3. You're going to need 1/3 as many nitrogens as you need hydrogens. Another way to put these numbers together, you're going to make 2 ammonias for every 3 hydrogens, or 2 moles worth for every 3 moles worth, or 2/3 as many ammonia molecules will form as you have hydrogen molecules. And then another way to think of it is however many nitrogen molecules you have, you'll make twice as many ammonia molecules, assuming you have enough of the hydrogen. So anytime you're looking at this recipe, it assumes you have enough of the other element or compound to make what you're going to make. From the book, they use, again, given and wanted. I used given and asked for, same difference. You're going to start with some number of moles of your given substance. That mole ratio, again, comes from the balanced equation. However many moles of the wanted substance per however many moles, these are just variables of the given. And then that will tell you how many moles of your wanted substance you can make. So they combine the X and the B divided by A. And you can do that if you want, but it's not necessary. Okay. Again, I like to say ask for instead of wanted. Most of the time in the laboratory, what are we going to be doing? We're going to be measuring mass because we have balances. Ours are electronic, but the triple beam balance works just fine. You're going to measure things out in grams, and so you have to convert it to moles first. This is from your book as well. How do you solve a mass-to-mass problem? Normally, you're going to want a certain mass of product, and you need to know the mass of reactant, or vice versa. So grams to grams is the most common type of stoichiometry problem. First step is always to change whatever you're given into moles, the mass into moles. So you're going to divide by the molar mass of that substance. You're going to figure out how many moles of given go with how many moles of the wanted substance. Wanted goes on top, given on the bottom. That comes from your coefficients from the balanced equation. And then finally, you're going to change moles of your wanted substance into grams of that substance. This is the rest excuse me, of the mole roadmap information, and I'm going to go through that with you in a separate little video. Okay, again, most of the times in a stoichiometry problem, you have to convert whatever you're given into something, from something into moles. You're going to find the mole ratio from the balanced equation, and then usually you're going to have to do that one more step, changing the moles of the wanted substance into something else, whether that's grams, whether that's liters, whether that's particles, it doesn't matter. Sorry, here's the slide I was thinking of. So this is our roadmap. Remember, whenever you're starting out with particles, grams, or liters, you're going to divide by something to get to moles of your given substance. And then once you have moles of your wanted substance, you're going to multiply by something, depending on what you're trying to convert to. Again, most of the time you're going to take one of these, go through moles, and come out at a second one. It's a multiple step problem. And here's an example. You can write this down and give it a whirl. Carbon disulfide and 3 oxygens combine to make carbon dioxide and 2 sulfur dioxides. That's how this reaction would be stated. So the question is 27.9 milliliters of oxygen reacts with carbon disulfide, so that's our reactant side, and they want you to calculate the volume of sulfur dioxide produced. If we're doing anything with volumes, we have to assume the conditions are STP. 1 mole of any gas at STP is 22.4 liters. Next thing you have to do is convert that given substance into moles. And in this case, this is a classic trick. They give you milliliters, not liters. So you actually have to do some metric conversions first. It's usually not terribly hard, but keep that in mind. So first thing I'm going to do, 27.9 milliliters divided by 1,000, right, will give me 0.0279 liters when I round it to 3 sig figs. When I multiply, when I take that number of liters and change it into moles, I have to divide by 22.4, and I get 0.00125 moles of oxygen. Of course, that would be 1.25 times 10 to the minus third as well. Go back to the balanced equation to find the ratio of the asked for substance to the given. There's 2 sulfur dioxides formed from every 3 oxygens, so 2/3 as many. Going to convert the moles of the given substance into moles of the asked for substance by taking the 0.00125 and timesing it by 2 and dividing by 3. We get, this would actually be 8.33 times 10 to the minus 4th moles, but I wrote it out. And then finally convert into volume, because it asks for volume. So we're going to convert our asked for moles into liters. It doesn't say to do it in milliliters, so I'm not going to. Sorry about that. So this time we're going to multiply by 22.4 instead of divide by it. And the answer comes out to be 0.0187 liters, which of course is 18.7 milliliters if you wanted to go that far. And that's the end. It's chapter 12 in section 1 and 2. I kind of put them both together, and so that is it for today.